This video is an introduction to Lisa Randall's Knocking on Heaven's Door. And a big part of the book is it talks about scale, that when you're studying theoretical physics, that you need to know what scale you're talking about, because there's different laws and there's different ways of perceiving and thinking about these different scales: the very large, the small, and then the extremely small. So on the large scale, um, she claims that the known universe, again, similar to the way Paul Davies thought, and this is a scientific fact, the known universe is 10 to the 27 power in size. And the way that that's determined is because of the speed of light times 14.3 billion years. You know what the observable universe is. Anything outside of that would not be observable. So on the large scale, all of the laws that apply are the deterministic Newtonian laws that were developed and that we operate in on a day-to-day basis. So this pretty much is the normal world that we live in. Our scale, she says, is we view things on a scale of about 1 meter, and the laws at this 1 to 2 meter uh, level in which we live in as human beings, all those laws apply to the extremely large universes, planets, gravity, how all that cause and effect functions. So the next level of laws, and they're completely different, is that at a scale of 10 to minus 19. And that's where the Large Hadron Collider in CERN is going to study particle physics this year. And we're going to get into a lot of what they're looking at. And at that level, that small, the different laws are counterintuitive to these laws at the large scale, and it's the quantum mechanics, where probabilities and chance and a lot of other laws apply. And that's why a big part of this book talks about scale, is that you need to know, am I looking at this larger scale? Am I looking at this extremely small scale? Or, and she also talked about another extremely small scale where another set of laws potentially can exist. And that's at the smallest of smallest, possibly at a Planck unit, Planck size, string theory type size of 10 to the minus 35 power. And at these levels is where they believe that you may unify the laws of quantum mechanics and Newtonian mechanics into what's called quantum gravity, where all four of the forces may be united. An interesting statement she said was that below this 10 to the negative 35, that space stops. And below that, space and time and laws, again, are going to be completely different beyond that. But our minds cannot understand how space could stop at that lowest fundamental level. Distance stops at that point. So that, and this was stated back with Planck back in 1900, that he theorized that there was this most fundamental unit, and below that, space and time stops. Um, at this point, we don't have the scientific capability of studying string theory. Everything is theoretical at this point. But The interesting thing is that Lisa Randall believes, and she's a PhD theoretical physicist from Harvard. Um, she believes that if we can ultimately study string theory and space at this smallest level, that because the space is so small and the energy is going to be so high to study this, that we potentially can create a black hole while we are doing those studies. The Large Hadron Collider, um, uh, the particles are uh, moved in a very fast rate and very high energy, and they collide and they create other matter. And she believes that if we get even smaller, that was at 10 to the minus 19, if we get to the most fundamental string theory level of 10 to the minus 35, that we could potentially create a black hole. And so that is really an amazing thing. And even beyond that, then potentially um, other dimensions may exist. So um, again, this is completely counterintuitive to the regular way that the general public and we operate in the world. So this is why she again refers to scale, almost like an artist would view scale. You view one thing from a larger area, smaller areas may be more detailed, and that these laws vary uh, by the scale that you're operating in and perceiving. So, again, all of this relates to perception and perspective. So she tied this a lot to an artistic way of viewing the world. As a matter of fact, they put together an uh, artistic exhibit on display. I think it's in New York, and that have a lot of these different perspectives to the pieces of art that she collaborated with about 10 other actual artists. So it was kind of interesting to see a theoretical physicist um, team up with artists to try to draw out this idea of perspective and perception. And again, this is the study of reality, and it goes back to um, the Eastern way of thinking, that the study of reality and the self and perception, all this kind of ties in together. So that's really interesting. She talks a lot about theory and trying to predict the future of how where theoretical physics is going, what types of things are possible, what things we might find, and where all this is leading in years to come. To come, and it's interesting. I almost sense that now she's a PhD in theoretical physics at Harvard, that she almost had to justify some of the positions that she takes and others take because they can be so far out there in their theories. So it takes a lot of creativity. This, you're studying or looking for potential theories, and ultimately it turns into an actual experiment that you can measure and so forth. But all along the way, um, you may come up with some crazy ideas, or various people may come up with what are viewed as crazy ideas, but you got to keep moving forward. It was thought that physicists could come up with this theory of everything, if, especially if this quantum gravity string theory, all the forces could be unified. And she stressed that even if we get to that point, then the tools would be laid so that you could study the universe more in depth. Just getting to that point won't be a knowledge of everything in the universe. All the answers won't be there. but the tools may be there so that then you could potentially move towards the theory of everything and an understanding of everything, possibly in this closed system. So that's really interesting when you think back of Gödel's incompleteness theorem, the Eastern way of thinking, how they believe that we could never know everything. Paul Davies believes that there would be an answer. Um, Others think that there's no way you could ever get to the ultimate answers. So that's going to be kind of interesting as everything moves forward. Um, Again, just statements. Matter is almost completely empty. That's at the foundational level. Atoms. Uh, we view this table as being hard, and the way we view the world. But below that, there is this counterintuitive foundation of atoms, and then what atoms are made up of quarks and so forth. Um, that it's completely different from the way we view everyday existence. So, um, just again, using to move forward with a creative theoretical these ideas, it takes an unintuitive mind to get into these other realms of where the laws are different at this level, the laws are different at even the smaller levels, and mathematics can get you there. But conceiving of it in our mind, especially when you talk about another dimension, that is just something that we can't visualize at all. So we have a standard model of the way we view physics and the way we um, function, and we make TVs and electronics and operate in the world, and science functions. But then you also have to have this creative courage to go through with these theoretical ideas. So some of the things that they're going to do at the Large Hadron Collider is they have high energy collisions. Um, uh, they're looking for a 1 in a trillion event, like hitting the lottery of the possibly something unique happening when this when these studies take place in CERN. And when these collisions occur, it creates particles, it creates matter, and it creates mass. So that's really interesting when you think of the theory of creation of the entire universe. Here, we're creating a machine which is creating reality. So this is almost like playing God. Some other interesting features that you mentioned was that it was extremely cold in the Large Hadron Collider. It's 1.9 degree above absolute zero. So kind of like here where we had our smallest Planck unit of size, where we want to ultimately study with string theory, there is an absolute zero, uh, lowest level to freezing as well, which is somewhat interesting. This is colder than outer space is in the level at which the CERN is, uh, Large Hadron Collider is operating in. So all of this is based on Einstein's E equals mc squared. Um, so with high energy, you can create uh, mass in particles, and so that's all amazing stuff. So some of the things that they're looking for is why is gravity weak, especially at these smaller levels, because they're trying to unify all four of the forces, so that would lead to the theory of everything. Other things they're looking for is possibly extra dimensions. Um, so that'll be interesting, especially string theory demands um, that there would be up to 11 dimensions, again, that the human mind can't conceive of, but mathematics can and theorizes that it is out there. Um, Einstein's theory of gravity um, works in more than 3 dimension, and so does string theory. So a lot of these mathematical theories will work, but it just seems very counterintuitive to how everyday thinking takes place. So you have to have this faith almost in theoretical physics and mathematics. Um, Here was a statement by Lisa Randall: dark matter is 6 times stronger than matter, but it doesn't interact with light. I found that really interesting. Light is so important, like in the double slit experiment and the quantum collapse, and how matter is created, comes into being. And dark matter, which is about 75% of the entire universe, doesn't interact with light. So it's something entirely different. So they're looking for more explanations of dark matter. Um, After these collisions occur, what they really find is particle decay. What the debris is, what is left after the fact, and they have to connect the dots and theorize from that. So other things, there was related to warp passages. She talked about these other dimensions possibly being in these brains uh, within our world. Everybody thinks that it's so small and we just can't see it, but it may or may not be small. She says that it just in some way just not may not be perceived. A lot is similar to how gravity may not um, be effective at a certain size, but then it is effective at other size very near to it. Possibly our perception uh, of other dimensions may just be slightly off in these brains, almost like this term comes from membrane, kind of within. So all of that is being studied and looked at and theorized, and it'll be interesting to see how all this moves forward. And then in the end, of course, it is the study of reality, and ultimately, it needs to be real uh, with ideas and human conception of it. So the theory ultimately will get proven and measured, and that's how we'll move forward.